Something that, again, you touch on very, very briefly at A level, but not very well, are 5 and 6 electron groups. Now, of course, you can't, in theory, even draw Lewis structures for these, because certainly WJUC specs didn't want you to go higher than common sense. Okay, but of course now you know how to do these, so thus some examples of species in which there are 5 groups of electrons around the central atom would include these ones. So if you look, I've sort of drawn them very, very crudely, in which I actually draw the lone pair as being an atom, but just to point out the shapes there. So phosphorus pentachloride, phosphorus with 5 fluorines, so this is 5 and O, 5 bonding groups, no lone pairs. SF4, 4 bonding groups, 1 lone pair. IF3, 3 bonding groups, 2 lone pairs. And XEF2, 2 bonding groups, 3 lone pairs. You can also draw ones that have 6 groups of electrons. SF6, 6 bonding groups, no lone pairs. IF5, 5 bonding groups, 1 lone pair. XEF4, 4 bonding groups, 2 lone pairs. And then the pseudo-imaginary anion XEF3 minus, 3 bonding groups, 3 lone pairs. Assigning our VSEPR considerations to these, so expanding the chart out. When you have 5 groups of electrons, the geometry is so-called Trigonal Bi-Pyramidal. Here is an attempt to draw it, and here is a pretty little picture taken by one of my students a while ago. So you see you've got the phosphorus in the middle, 1, 2, 3 atoms in a trigonal plane. That's 1, 2, 3 in a trigonal plane, 1 above the plane, 1 below the plane. And that, of course, if you have 5 bonding groups, no lone pairs, so that's PF5, that would, of course, be the shape. The angles in a trigonal bipyramid, 90 degrees and 120 degrees. 120 degrees within the trigonal plane, that's there, there, there. 90 degrees to the ones on top and below. Now go to SF4, that's 4 bonding groups, 1 lone pair. And this is a cute one because it's the first time where you have to debate which you take away. Which of those bonds do you turn into a lone pair? Because we have what are known as axial positions, top and bottom, and equatorial, going around the waist here. The trigonal planar are the equatorial, the top and bottom are the axial. Now we'll talk about this more in class, but the reason, for reasons of repulsion, minimizing the repulsion between lone pairs and other groups, it's an equatorial one that gets taken away. So you have this picture here called a sawhorse or a seesaw. Right, the fancy word that I've never used in my life, disphenoidal for that. This is kind of what it looks like. You see we've taken away one of those equatorial positions there. Okay, so now there's still close to 180 there, and then you've got these other ones, the 2 left from the plane. So the angles in there less than 120 and less than 90, because now you've got the lone pair repelling all of these groups, making those angles a little bit smaller. IF3 had 3 bonding groups and 2 lone pairs, and so the structure for that is a so-called T-shape, because you lose another one of the equatorial positions. So I believe I've got a picture of it there. So one equatorial position here, one equatorial position back there, both occupied by lone pairs. Angles in the T-shape, we draw it ideally as 90 degrees, but they're less than 90 because of the repulsion of the lone pairs. And then XEF2, 2 bonding groups, 3 lone pairs. What happens there is you just lose the last equatorial position, so it is linear, and the angles are exactly 180 because the lone pairs cancel out. You got ones, if you think about this particular shape here, you got lone pair there, and lone pair there. They're all repelling, but their repulsions cancel out. So this is a perfectly linear molecule, XEF2. Go now to 6 electron groups. I believe most of you learned that that was octahedral. They used to play these games called jacks in the States. I don't know if we still have them here, where they take perfect little octahedra like this and throw them around on the ground and try and pick them up and do stupid things like that. Three-dimensional coordinate axes, the X, Y, Z axes, however you want to think about an octahedron. If you've got SF6, 6 bonding groups, no lone pairs, perfect octahedron, the angles are exactly 90. Now in this case, when you take one of them away, so you've got 5 bonding groups, 1 lone pair, the example for that was IF5. It doesn't matter which one you take away because they're all equal in an octahedron. But then when you do take one away, now again you have gone to where you've got axial, that's the one opposite the lone pair, and equatorial here, the ones that are in the plane around the lone pair. This shape is called square pyramidal. There is a picture of it. Not an amazing picture because you can't really get the full effect that this is a square on the base and this top one at the top here, right? An ideal square pyramid are of course the ones built by the Egyptians. When you have IF5 or other molecules though, because the lone pair more repulsive, the angle is slightly less than 90 degrees. XEF4, 4 bonding groups, 2 lone pairs. Well, now you take away the other axial position, so you're just left with a perfect square planar geometry, and the angles in this are exactly 90 because again the effect of those lone pairs pushing cancels out. 3 bonding groups, 3 lone pairs would be T-shaped, and again angles less than 90, and such a molecule has not been made that I'm aware of, but 2 bonding groups, 4 lone pairs would be perfectly linear, angle of 180 because again the lone pairs cancel out.